Okay, off we go. So last time we were talking about the average value of a function, and reminder, this idea of average value of a function is based on the idea of a weighted average, and we just use size in the domain as the weights. Other than that, it's pretty much the same idea as a weighted average. So the single variable example I sort of waved my hands at last time. This is just plugging in directly into that formula, and give it a try. Make sure you can crank that out. It's pretty straightforward single variable. We're going to talk now about a multivariable version of this. So now this does look different, right? But again, I'm just using size as my weights. Now this time, if you're talking about a two-dimensional domain, right? Your domain's living inside of R2, size is now area. And adding up over the entire domain is now a double integral instead of a single variable integral. So a lot of it very analogous and just sort of adapted again appropriately to the context. So for example, if you want to compute the average value of x squared on the unit disk, then area, being as we're talking about the unit disk, area is just pi, right? That's an easy one. And then we have this double integral to be computed over that unit disk. Double integral where, color. X squared is our integrand, and we have a double integral to compute. Okay. Now, how do you compute this double integral? Well, suit yourself. A pretty good choice is to use polar coordinates, and that's what I've got here. So make sure to think that through. Do notice, I like to point this out whenever I can. Don't forget your stretching factor, right? Don't ever write dr d theta by itself. It's always r dr d theta to avoid forgetting it inadvertently. And then you just have an integral, and again, off you go. Easy computation. Okay, is everybody okay? Okay, moving along. So why all this business about weighted averages and average value of a function, etc.? Well, there's an important physics application called center of mass. Comes up in a lot of areas in physics. And this is not a physics class, so I'm not going to spend a lot of time talking about that kind of stuff. But a really nice way to think about it is that it's weighted average of position. So if you have a solid that's taken up a lot of space, where is that solid? Well, it's in a lot of places. It's taken up a lot of space, so there's a lot of different positions of a lot of little pieces of mass throughout that solid. So a weighted average of position, the positions are what we're averaging. Where the little pieces of mass are is what we're averaging. And we're taking a weighted average where, of course, the masses should be those weights. So, pretty natural idea, really. Right? Now, what it's good for physically? Now, that's a physics class's problem. But I will point out, here's another really nice way to think about center of mass, and that is that it's the balance point. It's where the total torque is equal to 0. In particular, then, this point right there has the feature that if you look at that amount of mass connected to this amount of mass, and if you ask how do I make it sort of balance perfectly? In other words, if you look at the counterclockwise torque that the first mass creates, and then if you look at the clockwise torque the second mass creates, when you have your finger exactly at the point defined by that formula over there, the weighted average of position, center of mass, what you'll find is that the total torque is 0. In other words, that it balances. Now that's a little exercise, by the way, and if you know what torque is, and if you've seen that physics before, then you can literally write down torque equals 0, solve for x bar, you will get that formula right there. Okay, so in general, of course, we're not looking at one dimension at a time. So weighted average of position, will look a little differently if you're talking about mass distributed over an entire area, for example. Right? And so that's your sort of updated formula for continuously distributed mass. And now the weird thing about that formula is this integral, namely this integral right here. Notice that the integrand is a vector, and we have not seen before how would you do an integral when your integrand is a vector. That's a little scary looking. And here's the good news. It's exactly what you would hope it would be. A vector just has coordinates, and you just do the integral one coordinate at a time. It's nice and convenient. And so in particular, with this 1 over m distributed, this integral just has coordinates like that. You just integrate the coordinates one at a time. So, nice and easy. Okay, so let's see an example in practice. We are going to look at this shape here. Let's see here. This shape here looks about like that. I want to know where the center of mass is. Now, real quick, I'm going to point out that in this example, I'm using density to be 1 just to make the integrals work out a little bit more easily. It doesn't have to be 1. It doesn't even have to be constant. In general, sadly, very often the density is not constant, and so that'd be an extra factor in there. But in this example, just to keep it reasonable, here are the two formulas from above. The x-coordinate of the center of mass be computed by that expression, and the y-coordinate of the center of mass by that expression. And this, again, just copying straight from above. Now let's talk about how to compute them. As y'all will recall, I'm a big fan of symmetry arguments. Symmetry arguments, very, very powerful. They come up a lot. And in fact, this first integral is 0 by symmetry. And I'm going to leave it to y'all to supply the details. Make sure to think through those details. As I like to say, therein lies the devil. The details really matter. So make sure that you can, in fact, supply those details. Remember 5 conditions I want you to write down, at least for exam 2. We'll discuss other possibilities later. So here's the dangerous one, though. The dangerous one is the y-coordinate, because it looks like it's susceptible to a symmetry argument as well. It isn't, but it looks like it is, and that's the danger. So whoopsie. Let me make a good color choice. The domain has a symmetry. It's symmetric over the y-axis. That's nice, right? The integrand looks like it's odd too, and the even more dangerous thing, it is odd. You see it has an odd exponent, 1. It does have an odd symmetry, but for y to be odd, we would need the reflection to reflect like that, which is, of course, through the x-axis. So this is an example, a naturally arising example of the landmine example that I showed y'all back in the last section, where, odd symmetry and symmetric domain, but with different axes. And so there is no symmetry argument. Any claims of a odd symmetry argument applying to this example are just wrong, and by the way, sort of obviously wrong, because this y-coordinate of the center of mass, just use your physical intuition. It's obviously not 0, right? The balance point for a shape like this, it'd be, I don't know, somewhere along in there. Clearly not down here, right? So again, be very careful, please, when you're using symmetry argument. Much as I love them, they are dangerous. Okay, now another thing I like to talk about when we are doing this is looking at this double integral and looking at your 2 options of how to compute. How would you choose between these 2 options? As said differently, how would you decide which way to order your differentials. And I've given you all a couple of kind of loose suggestions of things that you can do. Try not to slice through corners. Okay, well, neither one of these slices through a corner. So they're equally good in terms of the corner issue. Try not to force yourself into having to solve for a variable that makes the formula nasty. And again, they're kind of equivalent in some sense. In both cases, you have square roots on your inside bounds, which means in both cases, you would think you're going to have square roots in your outside integrals. So that's not really much of a giveaway either as to which one of these is better. And yet, in this case, I have a significant preference between these two. And this is really hard to see coming. You kind of just have to write it down and notice it, and then after you've been around the block enough times, you'll start to see it coming in advance. But you really just have to write it down. Look at what's happening here. My very first antiderivative that I take will turn this y into a y squared. I'll be plugging a square root into a square, which makes the square root ugliness disappear, and it's all polynomials from there. And so that second integral, I think, is quite a bit nicer and more convenient to evaluate. The one on top is not that bad. It just ends up being a u substitution, but still, all else being equal, I think the second one's nicer. Everybody okay with that? So just another thing to be on the lookout for if you want to, streamline your life. You want your computational life to be as convenient as possible. Okay, moving along. So, this is another application where I do have to point out that this is not a physics class. So I'm not going to be presenting this as I would in a physics. I'm going to leave out a lot of the physics. Right? I'm going to say a couple of things about the physics. But this is a nice example of how we can get tremendous value from one of our important math ideas in this course. And the big important idea I want to talk about here is accumulation. So there are various quantities where the whole is the sum of the parts. And what we're about to find here is that and I don't want to give away the game too soon, but there is a question we're about to ask, the answer to which is going to involve realizing that it's an accumulating quantity. Okay, so now a little background before we get into it. I hope you all remember your high school geometry. There's a relationship between arc length and central angle by way of the radius. So again, classical, standard high school geometry. Make sure you're good with that. And then taking a time derivative of both, what we end up with is a nice relationship between what I'm going to call linear speed and what I'm going to call angular speed. So the distinction, I call this linear speed because this is the rate of change of a linear measure of position. And I'm going to call this here, this omega, I'm going to call this angular speed because the time rate of change of an angular measure of position. You can keep track of where you are as you rotate around an axis by that angle. So angular instead of linear. It turns out this is a really useful idea, and just a quick cultural point, very often this gets called angular velocity. And that just kind of rubs me the wrong way because velocity is supposed to be a vector. This is clearly a scalar. Speed, I think, is the better term. Anyway, it's a minor quibble. Just heads up, you're going to hear people call this angular velocity. Okay, so very useful, this idea of angular speed in a lot of different settings. Okay, and with this background, now I want to ask this question here. How would you compute kinetic energy as you have some particle, let's start with, and it's moving around an axis. It has a certain velocity. How do you compute the kinetic energy? And of course, that's an easy one. 1/2 mv squared. By the way, if you're not familiar with kinetic energy, or there's no physics prerequisite in this course, kinetic energy is just a way of describing how much of what we use to get stuff done is represented in the physical motion that a particle is doing. So it's 1/2 mv squared. It happens to be the formula, and it's a long, complicated discussion as to why that is the right answer there. Okay, but energy is just what we use to do stuff. Okay. All right. So here's the harder question. Let's suppose I don't have a point mass. Let's suppose I have a lump like that. And this entire lump is rotating around that axis. So this entire lump is moving. Okay, well here's the thing. This little piece of mass right there, in one rotation, that little piece of mass doesn't move very far. But in that same amount of time, in that same single rotation, this little piece of mass there moves a much greater distance. Said differently, this little blue chunk of mass isn't moving with as much speed. This red chunk of mass is moving with much greater speed. So I cannot use this formula to compute the kinetic energy of this lump rotating around that axis. Because velocity is, speed, see, there I did it. It's easy to accidentally mess that up. Speed is not a constant over that entire lump. Everybody see the problem? Here's what's nice. Even though the linear speed, v, is not constant, the angular speed is. Every object in this entire lump makes 2 pi, change of angle per rotation because, well, that's just, rotation means that a full turn is an angular change of 2 pi. So what we're going to try to do is to rewrite our kinetic energy formula in terms of angular speed. So, okay, with all that noted, here's where the math comes in. And that is, let me do this. Okay, so this lump here, I'm going to make the argument that the kinetic energy is an accumulating quantity. This entire lump, I can chop that up into itty-bitty little pieces. Each little piece of mass will have some kinetic energy. And the total kinetic energy is just the sums of the kinetic energies of the little pieces. So now that's just an assertion. I think it's a pretty satisfying assertion, but the whole is the sum of the parts. Everybody okay with that? And that's the foot in the door to let us really answer this question comfortably. Because let's see here. Let me look at each little piece of mass now. Let's look at this one right here. That little piece of mass. How much kinetic energy is there in that little piece of mass? Well, whatever. It's on that little piece of mass. It's small. Every little part of that piece of mass is moving at the exact same speed. And when all the mass is moving at the same speed, 1/2 mv squared. Nothing to it. And having made that key observation, now you can fiddle around with the algebra a little bit. And this is algebra that y'all can think through. It's just a matter of moving things in and out of the integral. We get down to this as our formula for kinetic energy to replace this formula for kinetic energy right there. So again, this is what you might call the linear formula for kinetic energy. This is a different formula that's useful when things are rotating instead of moving in straight lines. Okay, now, really convenient thing happens if you just take this expression right here and rename it and just call it I. Now, instead of comparing that with this, now I'm going to compare that with this, and we've got a pretty strong analogy showing up. Linear kinetic energy, angular kinetic energy, kind of the same structure. 1/2 of something times one of our speeds squared, right? There's a lot of analogy in between these two formulas. And in the same sense that omega is the angular analog of speed, likewise, it makes sense to view this thing called I as an angular analog of mass. So this is a nice way to think about moment of inertia. And why do we care about moment of inertia? What's the point to moment of inertia? Well, in this, when you're thinking angularly, moment of inertia computed by this expression, typically denoted with an I, is an angular analog of mass. It plays the role that mass would have played, but in this angular context. Yeah?
How would you integrate the radius squared with respect to mass?
Yeah. Okay, so you got to keep in mind that this is, let's see here, great question. This is not representing an M axis, right? This is Riemann sum shorthand, right? So it's a little sloppy. It's arguably not quite. It's arguably a little awkward, but it's very, very common. What we mean by that in this case, let's see. Let me write this down over here. dm is just density times dv. Yeah, that's all it is. Is that cool? Yeah. Yeah. Good question. Okay, so that's the physics. But, again, a lot of y'all are engineers. I think it's going to be very important, what moment of inertia is. By the way, a real quick application. I know y'all are very interested in applications. Cars, kind of a big deal, right? They have wheels. I mean, right? Right? And so what do wheels do? They rotate. There's a lot of energy tied up in the rotation of the wheels as cars drive around the road, right? And as y'all know, of course, making cars as efficient as possible is kind of a big deal. And efficiency means we want to get as much, we want to be able to cover as much distance as possible, right, per unit energy. So we want to use as little energy as possible. So knowing how much energy is just going into the wheels rotating, right, is important. It's a significant factor in thinking about, gas mileage. Right? So how are we going to figure out how much kinetic energy is involved in the wheels rotating? Well, we're going to need this rotational formula for kinetic energy. Therefore, we're going to need to understand moment of inertia. So very important in lots more to say about it, of course, but a very important application. Okay. All right, now here's a little subtlety that messes up a lot of students. Remember, I set things up as per this drawing. In particular, R was distance to the axis of rotation. So this R right here, very commonly misunderstood. A lot of people see this R and they're thinking, oh yeah, cylindrical coordinate. Distance to the z-axis. Not in this case. And a case could be made that it's an unfortunate choice of notation, and I kind of agree with that, but this is extremely standard, so it is what it is. You're going to encounter this problem, whether I like it or not. So what you have to remember is that R in this formula for moment of inertia means distance to the axis of rotation, whatever that axis of rotation might be. It might be the z-axis, it might not be the z-axis. So, for example, if you are actually rotating around the z-axis and you want to know the distance from a point xyz, what is that distance to the z-axis? Then yeah, cylindrical coordinates, totally, it's exactly what you think it is. But if you're rotating around a different axis, by the way, wheels on a car, not rotating around the z-axis, right? They're rotating around a horizontal axis, like this. Then the distance from XYZ to that axis is going to be a different formula. And you're going to get a different formula for R, a different formula for that, distance to the axis of rotation, depending on the particulars of your question. So it depends on what is the axis. It also depends on, what's the nature of the domain. Notice that if you're talking about an area that is entirely, in the XY plane, if mass is distributed across area instead of a volume, then the R, in this case, is just absolute value of X. And in fact, for that particular picture, I can see that X is always positive, and so for that particular picture, I could get away with saying just X. So anyway, there's a million different versions of this. I wrote down 4 just as a for example, right? But there's lots of different versions of that formula. So please don't memorize a bunch of formulas for what R is. There are too many. Any list that you can feasibly memorize will be insufficient. So rather realize that the R problem is always just a geometry problem. Draw your picture, identify the geometry problem, solve the geometry problem. Okay, so let's see an example. Here we go. We are looking at this domain right here. On which there is a non-constant density. So the way that mass is distributed across area on this is, like I say, not constant. So given by that formula right there. Density depends on position. And with that said, this is going to be rotating around the x-axis. Here's our x-axis down here. And so that said, what is the moment of inertia? In other words, as this mass is rotating around this axis, well, we're going to be able to ask questions about kinetic energy. If you're interested in kinetic energy, you need the moment of inertia. What is that moment of inertia? So, okay, well, generically, really, really important formula to make sure you have memorized. Moment of inertia is always an integral of r squared dm. Integral, appropriate to the nature of your domain. Here I have a two-dimensional domain, so this is a double integral. dm, again, meaning density times size. Size appropriate to our context. Here, dm is density times dA. And r, well, let's see here. Our r, well, we have our axis of rotation is the x-axis. A point, x comma y, from which we need to know the distance to the x-axis. This distance in green here, geometric appeal, you see the picture. What is the distance down to the x-axis? That's the y-coordinate. And so r here is just y. Yada, yada, yada. Details, computations. Is everybody on board? Okay. All right. Cool. So that finishes 5.6. Okay, so real quick reminder. I'm pretty sure you all already know this. Okay. Definitely already know there's an exam on Friday, right? You probably already know that the fair game material for the exam is already settled. It was settled on Monday, right? Monday's class was the last class of fair game material. And on Monday, we finished 5.5. We did not finish 5.6. 5.6 is not fair game for the exam, right? But all of 5.5 is, and so good luck with all your studying and all. Now, likewise, we're about to go on now to Chapter 6, and Chapter 6 is not fair game for the exam either. But of course, we're approaching the end of the semester. Exam 3 is not that far away, right? And this is, of course, fair game for Exam 3. Okay. All right. So, new kinds of integrals. We're going to talk now about what are called line integrals. And there's a couple of different kinds of line integrals we're going to care about. We're going to take them one at a time. I want to start off by recognizing a luxury that we've been enjoying for the last month or however long it's been that we've been doing integrals. And that is, all of our domains have been what I'm going to call dimensionally convenient. Think about single variable calculus. Single variable calculus happens on a one-dimensional real line. And the domains for those integrals are one-dimensional intervals. Double integrals happen in a plane, two-dimensional plane, and the domains are two-dimensional. Triple integrals happen in three-dimensional space, and the domains are three-dimensional solids. So the dimension of the domain has always been the same as the dimension of the world that they're sitting inside of. And that's what we're going to let go of now. We're going to ask the question now, what if my domain is a curve such as that, which I claim is intrinsically one-dimensional? A lot of people think that's two-dimensional. It's not. It's a one-dimensional thing. It has length. It doesn't have area. It's one-dimensional. But it lives in a two-dimensional world, right? And so if I were to ask a question, if I were going to, if I'm computing if I want to make some accumulation argument, adding up over a curve in the plane, or possibly a curve in space, what kind of integral would that be? Tempting to say double integral because we're in a plane, but there's no area. Right? Tempting then to say, okay, well, I guess it's a single variable Calc 1 integral, but no, Calc 1 never addresses any questions about curvature. And how is this? What if the domain is curving around in space? It doesn't address that at all. So this is a situation that we have yet to entertain. And that said, it remains that this is still a situation where very naturally stuff can accumulate. So let me give you an easy example. Well, here's a really easy first example. If you have a wire bent around in this shape, right? And if the wire does not have a constant density, let's suppose the mass per unit length is kind of greater over here and maybe less over there or something like that. How would you compute the total mass? Well, I would want to chop it up into little pieces and look at the mass on each individual little piece and then add up over the entire thing, right? I would want to make an accumulation argument. I would want to have an integral of some sort, kind of like every other integral we've ever studied, but we don't. Here's another one that I think is amusing. I actually did a calculation like this once for sort of, just kind of personal fun. But I used to live in a house that was at the end of a very long driveway that I had to shovel the snow on. And that was a lot of work, right? I wanted to be able to brag about how much snow I moved, right? How many 1,000 pounds of snow did I have to go out there and deal with? I don't know if you've ever had that pleasure, but it's a lot of work. Well, driveways technically do have area, but nobody thinks of them that way. And just imagine a driveway of roughly this shape. It would be nightmarishly inconvenient to think about all the various, technically you'd have a little thin sliver over here, and then you'd have another, and there'd be various different corners and sides. It's intractable. Driveways we think of as being curves, and they follow curves. And what you can do, and what I did, is ask the question, on any given little piece of curve, if I were to look at, for example, this little piece of curve right here, how much snow was there on that short little piece of that driveway? In other words, on that, let's say 1 foot of the driveway goes like that, let's say. Over that 1 foot, well, there was a width, and there was a height, and then there was of that 1 foot of length, and then there's the density, and various factors you could write down, and I could tell you how much mass of snow there was per foot along the driveway. Right? And then, so on that little piece, you could argue on that piece that there was a certain amount of snow per foot. In other words, a certain snow per unit length to be multiplied by length. And then you can talk about okay, well, I'd like to then add that up over the entire curve. And so, you're going to have to figure out how that works, and we'll talk about that in a couple of minutes. But adding up over the entire curve gives us another Riemann sum. Okay. How are we doing? Everybody kind of on board? I know this is all kind of vague right now. Okay. So the important takeaway is that all these dimensionally convenient examples we've seen in the past were, arbitrarily convenient, but there are these dimensionally awkward cases that matter too, right? I need to be able to make accumulation arguments on curves, for example. And this is what such an argument would look like. It's a Riemann sum. It's slightly different, adapted to our little scenario here, but it is nevertheless a Riemann sum. What's going to eventually be our integrand, you'll notice, again, just like every other integral we've ever written down, is accumulated quantity per unit size. In this case, size is length. So, pretty natural scenario. Now let's just talk notation and terminology a little bit. Let's see here. So, hopefully no surprise, we represent summations with an integral symbol. We represent delta whatever with d whatever. Again, that's the same little standard shorthand we've used in the past. So hopefully that is no surprise and to be expected. This resulting expression then, don't lose sight of the fact that all it is a Riemann sum, right? But nevertheless, we tend to think of it as being this thing called an integral, and in this case, this is called a scalar line integral. And we're going to talk in a minute about how to compute it. The important takeaway right now is that a scalar line integral is an attempt to accumulate over a curve. Okay. Real quick, it's a bit of an abuse of the term line because, in fact, we're talking about a curve. So we just have to be flexible on that. Wouldn't it be nice if this is called a curve integral? But it's not. So anyway, we have to deal with that. Next question: why do we call this specifically a scalar line integral? And it turns out we're actually going to have, not yet, but very soon we will have two kinds of line integrals. This one is distinguished by the fact that the differential is a scalar and the integrand is a scalar. And you might be thinking to yourself, well, what in the world else could they be? And what we're going to find on Monday, right, is that the other kind of integral has a vector differential, which is a little scary. When you think about it, it's like, oh my God, what could that even mean, right? It's intimidating. And we're going to have a vector field integrand. And what does that mean, and how does this come up? And that's it's going to come up very naturally. It's nothing to worry about. But we call this a scalar line integral to distinguish it from what we'll see on Monday, which is going to be called a vector line integral. Okay. All right. Foreshadowing. Okay. How to compute it. Y'all remember change of variables. Change of variables is a clever strategy for dealing with undesirable domains. Now, why in section 5.5, what was it about domains that we found undesirable? Well, corners. Ugly equations of edges. Stuff like that. Well, here again, we have an undesirable domain. Now, this is undesirable for sort of different reasons. I'm going to say this is undesirable because it's dimensionally weird. It's not about corners. It's not about weird equations. It's that this is dimensionally out of place. But the fact that it's undesirable for a different reason doesn't change the fact that it's undesirable, and it also doesn't change how we're basically going to approach the problem. Just like within change of variables, we're going to figure out how to view our undesirable domain as an image, and then we're going to use the pullback and stretching factor strategy to take an integral defined on a curve, which we, again, don't know how to deal with, computationally, highly undesirable domain for an integral. We're going to figure out how to rewrite it as an integral that happens just on the t-axis. In other words, a single variable integral. So it's just another example of a pullback. It's just like change of variables with a few details changed. So, all right, now a couple of observations to make. What is this function? What is this function that makes our curve an image? And the answer is it's a parameterization. Lucky break. We already knew this. Think about parameterizations. What does a parameterization do? It takes input values of t, and the outputs are points on the curve, and as t increases, we trace out the curve. In other words, the curve is the image of that parameterization. So check on our first step. Parameterize the curve. In this context, parameterizing the curve plays the role of choosing an appropriate change of variables function. Okay, next we have to figure out how to do the pullback, which is just a matter of plugging in, really, except for the fact that we have to figure out how to figure out a stretching factor. In this context, the stretching factor says, what am I going to multiply by dt to get this little arc length ds, right? How is this size magnified to give me that size? Let me say that a little bit differently now. What do I multiply by elapsed time to get distance traveled? And this is actually an old physics idea that I'm sure y'all recall, and that is speed. Right? Our stretching factor here, speed. So distance is speed times time. Right? Middle school science class, hopefully an old familiar concept. Y'all okay with that? Distance equals speed times time? We're in business. Let's see here. Our ds from our scalar integral. ds is stretching factor, namely speed, times time dt. And let's see here. By the way, our parameterization itself is what allows me to rewrite x in terms of t. And so we are done with our pullback. And short version then, if you write down, in the abstract, if you write down some scalar line integral representing how much snow you shoveled or how much mass there is on a bent wire or whatever, any sort of accumulation that you might want to do over a curve, once you've got it written down in the abstract as a line integral formula for how to compute it, single variable calculus, plug and chug, nothing to it. Everybody happy with that? It's really clever how this all kind of fits together. Okay. All right. Now there's a little bit of a worry that I'm going to basically wave some hands at. I'm not going to deal with this formally or rigorously because it's just not what our course is. Math219 will do stuff like the following. Math219 is not going to do it. Here it is, the nasty, ugly little question. This depends on the parameterization. I can see the parameterization right there. There's lots of ways to parameterize a curve. I might pick one parameterization. You might pick a different parameterization. I'm going to get one integral. You're going to have a different integral. Whose integral is the right integral to compute what we want? What's the right parameterization to use? So here's the really good news, and this is proved in the book if you're curious, but it's not really part of the course material. This expression doesn't depend on the parameterization. You can use any parameterization you want. You'll always get the same answer. Any parameterization is fine. So nothing to worry about after all. Okay, let's see an example. I'm actually going to call this 4 examples. You can see right here. 4 little calculations there. We've got some specifications for a wire distributed, bent around in the plane. And the question says compute the mass, compute the center of mass, both coordinates, and compute the moment of inertia, let's say around the x-axis. So 4 separate calculations that we're going to do on that same wire. And these 4 calculations are down here, and we're going to walk through a couple of them. I'm going to leave the other 2 for you to walk through on your own as a, again, sort of nice exercise. So let's talk about the top 2, and let's fit this in about like this to start. Here's the good news. I'm just going to take this. Good news. All 4 of these questions are about the same wire, which is following the same curve, which is using the same parameterization for the same range of values of t over which density is distributed in exactly the same way. It's the same wire, so all of that's the same for all 4 of these questions. Same parameterization means we have the same velocity, and therefore, using the same formula for the stretching factor, we get the same formula for the speed. So all of that stuff that I have in green there is going to be exactly the same for all 4 of these questions. And it's really convenient to notice this because then you can do the calculations kind of in parallel with each other because they use so much of the same stuff. Here we go. Let's talk about mass. Mass is an accumulating quantity. Mass is the sum of little pieces of mass. On the other hand, and just to simplify my thing here, let's also talk about center of mass, in particular the first coordinate of the center of mass. We've already talked about that formula. So we have 2 different sort of starting point formulas because 2 different quantities. Yeah, sure, fine. But both of them mass is still density times size for both. The density that's given is the same for both. For both, we have distance equals speed times time. And let's see here. For both, we have already computed the same formula for that speed. So all of that's just a shameless ripoff. The second integral, I'm just basically copying from what I did for the first integral. So all that's the same. The only things that are different, of course, are the starting integrals. And then, by the way, furthermore, they share the parameterization. So don't forget, this right here is actually our formula for x. And so that x is t. And likewise in this other integral, these x's are just literally t. And then likewise, that's our formula for y. And so the y is t squared in both of these. So much that these computations have in common. They're practically the same calculation, just with a different starting integral, and so different resulting integrals. Okay, so I'm going to leave, as I said before, I'm going to leave it to y'all to think through by analogy these last two integrals. We'll draw the line right there. Y'all have a good rest of your Wednesday. See you on Friday for the exam.